Okay. Okay, quiet, please. Quiet, please. We're going to go ahead. So arithmetic was when you get the next term by adding the same number, right? We always recognize that pattern. And geometric is when you multiply to get the next term. For arithmetic, we basically had two formulas we had to know. The nth term of a sequence and the sum of a sequence, the finite sum of a sequence. For geometric, we have a formula for the nth term. We have a formula for the sum of a finite sequence, but there's also the sum of an infinite sequence, or what's called a series, right? The series is the sum of a sequence. That's something you don't have with arithmetic that you have with geometric. So geometric is when the ratio of consecutive terms is the same, meaning divide the second term by the first, and the third by the second, and the fourth by the third, and so on and so on. Every time, if you always get the same number, then that is called a common ratio, and the sequence is geometric. Okay, we're good with that. Same thing, right? So the first thing we've got, we'll go through a few and just see what they look like. Again, if I didn't tell you the pattern here, you'd have recognized it right away. You can see what's going on to get the next term, and you would have said the next term in that sequence is 32 and 64, etc. Right? They've already told us it's geometric, right? It's not a question. Is it geometric? No, they told us, and then they just divided one pair of consecutive terms, right? 4 divided by 2 is 2, right? So that 2 represents the R. Right? And then just like with arithmetic, because we did an example which was pretty close to this, right? Then they gave us a formula for the nth term. And whereas arithmetic always looked like it was linear, kind of like mx plus b, the n was raised to the first power, for geometric it looks exponential, right? The n is in the exponent, right? That's why when you increment n, right, if I let n increase by 1, you get one more factor of that number. So notice that r equals 2, and it's 2 that's being raised to the n power, right? It's always the r is whatever's being raised to the power, right? This one you can see they've already told us it's geometric. 12 to 36 looks like you're multiplying times 3, right? So 36 over 12 is 3. Common ratio is 3. And when I look at this formula right here for a sub n, again, where's the 3? It's what's being raised to the n power, right? The 4 is not. Don't make the mistake of multiplying 4 times 3, because you can't do that. And then even if it's fractions, even if it's alternating signs, right, you still do the common ratio. 1/9 divided by negative 1/3 is negative 1/3. I mean, it looks like you're multiplying. For the terms to change sign, that means you must be multiplying by a negative number, right? So that's why it's got to be a negative 1/3. And look at the denominators. They're going from 3 to 9 to 27 to 81. So that's why it's got the 3 in the denominator. But just divide them, and then that's the common ratio. And the formula is here. And again, it's the negative 1/3, the r, which is being raised to the n power. Okay, we have a formula for the nth term of a geometric sequence, and this is it. It's the same one we used last year. Right? an equals a1 r to the n minus 1. Right? So we know all the parts of that. Right? a1 is the first term, R is the common ratio, N is the ordinal number of the term, right? Whatever term in the sequence that it is. Notice that if you plugged in N equals 1, which should give you the first term, you would have an exponent of R to the 0, right? So then R to the 0 is 1, and A1 equals A1. So normally, if there is a number in front of the R being raised to a power, that's usually the first term. Not always, because it depends. It depends on what the exponent is. If it was just N, then it wouldn't be. But since it's N minus 1, then when you plug in N equals 1, you get R to the 0. So the main thing is just remember this formula. Right? Then this would be the explicit formula. Right? I don't think it even talks about the recursive formula. But if you wanted to write a recursive formula for this, what would that look like? I'll do it in terms of AK plus 1 equals AK, the term before it, times R. That would be a recursive formula for geometric. Okay. So, examples. Writing the terms of a geometric sequence. Write the first 5 terms if you know the first term and the common ratio. Right? Do we need the formula for that? Not really. If you know A1 is 3, right? Then the common ratio is 2, so what will the next term be? It'll be 6, right? Right, that is 3 times 2. And the next term will be 12. The next term will be 24 and 48. And you don't have to use that formula and plug it in 5 times, right? You know the first term, just keep multiplying. Okay, find the 15th term of a sequence whose first term is 20 and the common ratio is 1.05. Okay, so if the first term is 20, right, A1 equals 20. If we did what we did on the last slide, right, we would multiply by 1.05 to get the next one, right, that would be 21. And then you do it again and again, up to the 15th term. That's probably not going to be very easy to do. Every time multiplying by 1.05, this time I think I'd use the formula. Since they've given us the pieces of the formula, let's just use it. Right? The formula for the nth term would be AN equals 20 times 1.05 to the n minus 1. And if I want to find the 15th term, then just plug in n equals 15. Make it, and it'll be a one-step calculation, right? A15 equals 20 times 1.05 to the 15 minus 1. $39.6. Make sure, you need to be doing these things with the calculator and not just here, because when you use those yellow calculators, they may work different if you got then the 83 you might be using at home, right? Because when you're going up into the exponent, with those 83s, it's got to be in parentheses. With these things here, it doesn't. You need to practice it. Don't make the quiz or the test be the first time you realize you didn't know how to do that. Right, find the 12th term of the geometric sequence. Okay. This is a pretty easy bunch of numbers, right? No decimals involved here, no fractions. If it's geometric, what's the common ratio? It looks like it's 3, right? So R equals 3. So, I mean, you could definitely just multiply each one by 3, do it another 9 times, and you'd get it. Or you could use the formula. Personally, I'd use the formula. A lot less things to calculate if you do it that way, right? If you go AN equals, the first term is 5, the common ratio is 3, and it's raised to the n minus 1, right? Again, if you're asked for, in a problem, if it asks you for the formula, and then it says find the certain term in the sequence, make sure you don't just like in one step plug in the 12 and the 12 there, and you never wrote the formula with the n's involved. Because if it's a formula, that means it's going to have the n in there, so you can plug in any value for n. Right? A12 equals 5 times 3 to the 12 minus 1. And that is 885, 735. Good, good, good. Okay. The fourth term of a geometric sequence is 125, and the 10th term is 125 over 64. Find the 14th term. Okay, let me write out like we did on the last in the last section. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have the fourth. We have the 10th, 5, 6, 7, 8, 9, 10. And we want to know the 14th. Okay, 125 and 125 over 64. So in order to find the 14th term, what number do we need to know? The common ratio, right? I mean, if we're going to find that term by using our formula, then we need two things. We need the first term and we need the common ratio. But at the very least, we need the common ratio. So how do these two numbers help us to find the common ratio? Yeah. What's that? Not the average as you're saying it. Now, is there a way, you could like fill in this middle term by doing something like the geometric mean, right? Yeah, you probably could, but then you'd still need to fill in some of these. Instead, I would just say, how many times are we going to multiply times R to go from the fourth term to the 10th term? 6 times, right? To go from the fourth to the 10th, you must be multiplying times R 6 times. So we know that 125 times R to the 6th equals 125 over 64. Right? It's not 6R, it's R to the 6th. R times R times R times R times R times R. Okay, now that you could solve for the R. Right? Divide by 125. R to the 6th is 1 over 64. And then you need to find the 6th root of 64. And most of these things, they're using the common numbers that you would think. If you're not already familiar that 64 is 2 to the 6th, it is. Can you find the 6th root of something in your calculator? Right? In the math menu, you can do that. But in any case, R is 1/2. Okay, now, if we wanted to use the formula, that would be one part of what we needed. We would also need to know the first term. Okay, but do we really need to do that? If we know that the R is 1/2, how could I find the 14th term since I already know the 10th? Multiply by times R how many times? 1, 2, 3, 4, right? To go from the 10th to the 14th, you would multiply times r 4 times. So we would do 125 over 64 times 1/2 to the 4th equals. $125 over like 1,024. Yeah. If instead I was going to use the formula, then I would need to know the first term, right? Well, if the r is 1/2, that's telling me that they go from 120, the 4th term to the 5th term, I multiply times 1/2. How would I go from the 4th term to the 3rd term? I'd multiply times 2, right? So if I multiply this one by 2, I would get 250. Multiply again, I would get 500. Multiply again, I get 1,000. So it would not have been that hard to have come up with the A1 and then use the formula for the 14th term. Okay. Let me know if I go too fast. Okay, then we have the sum. The sum of a finite geometric sequence, meaning just a fixed number of terms. And this formula is one that you had last year. It's the same formula. It's up here, but I'll rewrite it here. S sub n equals A1 times 1 minus r to the n divided by 1 minus r. Okay, again, the S stands for the sum. The A1 is the first term. The R is the common ratio, and the N is the number of terms you're adding up. Right. Unlike the arithmetic, the S sub n, we don't need the last term. Right. We don't need it at all. We had a way around that when we did it for arithmetic, but still, this one, it's not even going to ask you that. It's all the things you can usually see anyways when you look at the first few terms. Okay, so let's find the sum of a finite geometric sequence. How do I know this one's finite? Yeah, I mean, it goes from 1 to 12. How many terms are we adding up? 12. Right. So let's see. We're going to use our formula. Sn equals A1 times 1 minus r to the n over 1 minus r. Okay, I have to plug in for A1. How do we find A1 when you're given the summation notation? Plug in what? Plug in the 1, right? If you plug in the 1 here, that'll be the A1. So A1 equals 4 times 0.3 to the 1 minus 1, which is 4 times 0.3 to the 0, which is 4. Okay, so we got to that. What is the R? In this formula right here, which is it that represents the R? Right? It's the R is whatever is being raised to the power, so that is 0.3. And then how many terms are we adding up? If it starts at I equals 1 and it ends at I equals 12. 12. So you can plug all that in. S12 equals 4 times 1 minus 0.3 to the 12th over 1 minus 0.3. These especially, a lot of times you'll get it set up like that, but then somehow you're going to mess up the math when you do it in the calculator. assuming you do it in the calculator. So just make sure, let me clear this. Make sure you put it in there correctly. I mean, definitely I'm putting in the 4, right? And now I've got to put in this here. Well, just make sure that you've got the numerator in parentheses and the denominator in parentheses, right? So parentheses, 1 minus 0.3 raised to the 12th. Make sure you get out of the exponent before you end the parentheses for the numerator. And then divide it by, and you need another set of parentheses, not that. Delete. Okay. Parentheses, 1 minus 0.3. Enter. Especially like if you're at home using 83, then that's pretty much what you're going to have to do. Just make sure you put parentheses in all the right places. When you're using these calculators, remember that we have a way to enter something as a fraction, and you wouldn't have the same issue. Right? If I do this, 4 times, and then I go alpha y equals 1, and now it's going to give me the fraction. So I don't even need parentheses now. I can just say 1 minus 0.3 to the 12th, arrow down to the denominator, 1 minus 0.3. And it looks pretty much like you've got, right? So just be careful about the numerator and the denominator being in parentheses. And remember, like, let's say you're doing a test question that's something like this. I mean, if you just show that you're plugging everything into the right place, I mean, that counts for something. If all you do is, like, show an answer and it's wrong, that's good. Okay. Now, for geometric, unlike arithmetic, you can actually add up, in some circumstances, an infinite number of terms. Right? And again, the example, I've used the example before of like walking from one side of the board to the other. Or let's just say if I make this box 1 long, right? Right. If I say I'm going to go from one side of the box to the other by going halfway to the end in each step, then in the first step I get halfway across, right? And that's 1/2. The next step, halfway to the end, is 1/4. The next step, halfway to the end, is 1/8. Right? Does that look like it's geometric? You know, what does it look like the R is? It's a half, right? Because every term is 1/2 of the term before it. Am I ever going to get to the end of the board? No, I'm going to get infinitely close, like a function's graph does to it gets close to its asymptote, but I'm never actually going to get to the end of the board. When that happens, you say that the sum is converging to whatever that value is. Okay, now, so the circumstances when you can do that are when the R is less than 1. Specifically, if the absolute value of R is less than 1. So you would say if the R is 1/2, that's good. If the R is -1/2, that's good. If the R is -2, that's not good. In that case, the absolute value of R is not less than 1. R is less than 1, right? But those terms are going to get bigger. They're just going to be switching signs as they do. So the formula for this is, it's really just a simplified version of the one we already know for the finite sequence. Right? If I take that one, Sn equals A1 times 1 minus R to the n over 1 minus R. I mean, this formula here is missing one term from that. Which term is it? The R to the n, right? And the reason is because if the absolute value of R is less than 1, if you take something like R equals 1/2, R equals 1/2, and you raise it to the n power, what happens if you let n become really, really, really large? I mean, what is 1/2 to the 1,000th power? something really, really small, right? As you raise a fraction less than 1 to a higher power, then that term basically goes to 0. So if you let the n go towards infinity, the formula you're left with is just that, which is that. Because the r to the n is converging to 0, that means your sum is converging to this. Okay. Easy stuff. So find the sum. We have two of them here. One of them is written in the summation notation, and one of them is written just as a sequence. Okay. In the summation notation, again, I'm going to use this formula, S equals A1 over 1 minus R. Okay. So the easy part is the R. What's the R? Yeah, the R is 0.6. And then how are you going to find the first term? You're going to plug in the lower limit. In this case, it's 0. It's not always. You got to just look and see what it is. But this case, it's 0. So when we plug that in here, right, that's going to tell us A1 equals 4 times 0.6 to the 0, which is 4. Right? And we already said the R is 0.6. So that's all you need for this. 4 over 1 minus 0.6. Right? Which is 4 over 0.4, which is 10. Right? Now, when you look at the second one, we could tell the first term because it's just written there. In that sense, that's a little easier, right? The A1 is right there. And then we have to calculate the R. How do I calculate the R? R equals, take the second divided by the first. Right, so 0.3 over 3 is 1/10. So that's all you need. Plug it in the formula. S equals 3 over 1 minus 1/10. S equals 3 over 9/10, which is 3 times 10/9, which is 10/3. Good. I didn't have any examples of this, but I just wanted to point it out. I think in the last version of this book they did. If you look at this first one, right, n equals 1 to infinity. If you were given that on a test, then you'd have to say, what is the value of R? 2.1. Okay, does that meet the criteria for being able to? No. So what you have to say, because this R, right, R is greater than 1, therefore this series doesn't converge. So if it's written like a summation, that's what you got to recognize, right? Don't plug it in the formula. You'll get an answer. If you plug in the formula, you'll get an answer, but it won't represent anything because it's actually not converging, right? In terms of if it's written out like this one is here, what you notice is that the terms are getting bigger, right? If the terms are getting bigger, what do you know about R? It's bigger than 1, right? Terms getting bigger. That means R is greater than 1. So you have to say it doesn't converge. one last one. Okay, an investor deposits $50 on the first day of each month in an account that pays 3% interest compounded monthly. What is the balance at the end of 2 years? Okay, this is called an increasing annuity. Really? I said, you're not much of an investor if you're putting $50 a month away. It makes it sound like some Wall Street guy. I don't think they'd be messing around with this. Okay, we have a formula for, what formula do we need for this? Compound interest, right? You need a compound interest formula. And, okay, remember the compound interest formula looks like this. The amount is the principal times 1 plus R over N to the NT. But at the end of the last, I think actually the 9.1, we had somewhat of a modified version of this that looked like this. A equals, and we're just going to fill in for some of the things that we can. It's $50 times 1 plus, the interest rate is 0.03, right? It's compounded monthly, so what is the value? In this formula, the N would have been 12, right? And then raised to the NT. In that formula that we used the other day, instead of saying it like that, this just said raised to the N, where N is now the total number of compoundings. It's not the compoundings per year times the number of years. It's just that represents the total number of compoundings. So we're not really interested in this one. We're interested in this one right here. Okay. Okay, so let's see. If you put that first amount in, that first $50, and you leave it in for 2 years, how many compoundings is it going to go through? 24, right? So the first term is going to be 50 times 1 plus 0.03 over 12 to the 24. Okay, but he's putting in that amount of money every month, right? Now the next month, he puts in another 50. How long is it going to be in that account? 23, right? One less month, because the whole thing, the whole period of time is 24 months. So the first amount is in for 24 months. The next amount is in for 23. Right, the next amount would be 22, 21, all the way until you got to 1 month before the end, and then that $50 would be in there for 1 month. Right, that'll be 50 times 1. That's not a good one. 1 plus 0.03 over 12 to the first. Okay, well, we could write that with a summation notation, right? This is the sum from n equals 1 to 24. Oh, sorry. Oh, that's right. N equals 1 to 24 of 50 times 1 plus 0.03 over 12 to the n. So that's going to be geometric, right? Because we have a number that's being raised at the end, kind of looks exponential there, right? That's going to be a geometric, a finite geometric at that. Let me see if I can do this. Nah. I'm going to go to the next slide. N equals 1 to 24 of 50 times 1 plus 0.03 over 12 to the n. Okay, so if we're going to do the sum of a finite, that means we're going to use this formula. Fn equals A1 times 1 minus R to the n over 1 minus R. Okay, and I need to know 3 things. First, I need to know the first term. How would I find the first term? A1 equals this thing here with a n equals 1. So it's 50 times 1 plus 0.03 over 12. Parentheses 1 plus 0.03 divided by 12. 50.125. Okay, I need to know the R. Okay, what is the R? It's this right here, right? R equals 1 plus 0.03 over 12. $1.0025, and I need to know the n. N equals 24. Okay, so that's everything we need. Plug it in. S24 equals 50.125 times 1 minus, where's our R? 1.0025 raised to the 24 divided by 1 minus 1.0025. Clear. I'm going to do it like this. 50.125 parentheses 1 minus 1.0025 raised to the 24. Get out of that. End parenthesis divided by parenthesis 1 minus 1.0025. Enter. 1238.23. Okay, well, how much money would you have put in at that time? $50 a month for 2 years? $1,200, right? So minus $1,200, how much money did you make because of this compound interest deal? $38.23. I mean, they have some other, I don't even know. The last book had other formulas in there that talked about, you know, people investing a certain amount a month and then people drawing money out at a certain rate too. I mean, people do these calculations, try to figure out how much do I need to save, you know, at which age am I going to retire, and then how much money do you think I need? Okay, well then I ought to be putting money away at a rate like this so that at the end of that time period, I've got that much money, right? And then you've done a similar calculation to see how does that money spend down as you get old like me. Okay, so that's it. Like I said, I'd say most of what we did in there was pretty much what you got last year. Maybe that last example was a little bit different. In fact, they don't really have any great homework problems that do just like that last example. There is one word problem, but it isn't like that one because they didn't like the problems they had. So that's it. You got 35 minutes. Get it done.